Welcome back to Chem 4300. In this video, we're going to finish up our discussion of chemical kinetics, and now we're going to look at reactions in solution. Now, when you think about a reaction that's taking place in solution, say between some molecule here and a molecule here, we know that in solution there's all these solvent molecules that are around the reactants that are going to eventually meet and react. Now, what these solvent molecules do is they can create a sort of a cage, a sort of a trap that allows the molecules, once they finally meet, to sort of bang into each other many times, and that increases the likelihood that they're going to react than if you imagine the opposite case when there was no liquid solvent around and they're all in the gas phase. So if in the gas phase these guys would collide, they would either react or not, and then they would go off. But here you can see they come together. When they collide in the solution, the solvent molecules hold them together and increase very much the chance that they're going to react. So if this reaction is fast enough, then the rate limiting step then becomes how long it takes for them to actually find each other in solution and for them to react. So we can write down the mechanism for this reaction in solution as the following steps then. First is A and B finding each other. So this is the diffusion of A and B into that solvent cage. Then we're going to have the possibility that, well, they might get into the solvent cage but then leave without reacting. So then they go back to A and B. And then there's a possibility that when they're in the solvent cage, they react and they form the product. So those are going to be the three steps in the mechanism that we imagine for this reaction in solution. So we'll write down that the rate of the reaction, the dP dt, is Kp times this AB together in the solvent cage. That's our intermediate, and we can make the steady state approximation, and we can write down that dAB dt, there's a missing D here, sorry about that, dAB dt is equal to, and you can look here that there's the formation of AB, which is Kd times AB, and then we have the loss of AB here by them going disassociating, so that's minus Kr times AB, and then we have the formation of the product, which is a loss, so we have minus Kp times AB, and in the steady state approximation, we'll assume that this derivative is going to be equal to 0. That allows us to solve for the steady state concentration here, and now we can go back to our expression for the rate for the product formation, substitute in our steady state approximation, and we'll get this expression here. Okay. Now, what we're saying is that this Kd is the rate at which they diffuse together, Kr is the rate that they go back to reactants, and Kp is the rate that they react. So we're going to say that the rate at which they react is much greater than the rate at which they go back to the reactants. And if we say that, then what we have is we can ignore this term, and we're left with a reaction rate that's just determined by the rate at which the rate constant associated with them diffusing together. So if I take that as my approximation for their reaction rate equation, then I can go back and look at what the diffusion coefficients are. And so this rate is related to the diffusion coefficients for A and B. So this is the diffusion coefficient for A, the diffusion coefficient for B in this solvent. Ra is the radius of the A molecule, Rb is the radius of the B molecule, and Na is Avogadro's number, and 4 pi are constants. So this is the expression for that rate constant that depends on the diffusion coefficients. Now, these diffusion coefficients you can get from something called the Stokes-Einstein equation, and that's equal to kBt over 6 pi divided by the viscosity and divided by the radius of the molecule. So this is the viscosity of the solution that we're working with, so the solvent that's around the molecules. And so we expect this to get smaller as the mass of the molecule increases. As the mass increases, the radius of the molecule increases, and so we expect this to get smaller. But let's assume, for argument's sake here, that both our reactant molecules have the same size and they have the same diffusion coefficient. In that case, then, all of this simplifies down to just this expression here. So substituting this into here and making this assumption, we get this very simple expression for the rate constant for this reaction is just 8 over 3 RT divided by the viscosity of the solution. So let's look at an example where you have a reaction taking place in water. We know the viscosity is 8.9 times 10 to the minus 4 Newton seconds over meter squared. What's the rate constant for any reaction taking place in water? Well, the diffusion, if it's diffusion limited, then the rate constant is going to be determined by this KD, and it's going to be given by that expression. We put in 298, we put in the viscosity down here, we get this for the rate constant. And it's that simple. So we expect then for reactions and solutions to be primarily governed by the diffusion coefficients, and that's going to be mainly dominated by the viscosity of the solvent, and we have a very simple way we can derive that. So that's it for this section on chemical kinetics, and I'm going to give homework assignments that will work in class, and they're going to be coming out of McCory's book. We'll be posting those online so you can get access to them. Here they are on the slide. The ones that are starred ones are the ones that we'll do in recitation and on Tuesday and Thursday. Okay, that's it for the material in this class.